Alrighty. Here we go. Can everyone see this?
Yeah, Colby, your voice is not quite as loud as it should be compared to other people's voices.
Sorry, what was that?
I thought your voice was rather low.
Okay. Is this better?
It is.
Okay. Might also need to... Okay.
Hey, Carolyn.
All right. And I guess let's go ahead and start. This is the Rethink Vent PSR presentation, the prototype status review.
These are the revised calculations. What you can see is the data collected. The calculations are done based off of the breathing rate. So whatever the breathing rate is set to is how we'll determine our cycle, which will be an inspiratory time and expiratory time. And then from that, we can calculate our tidal volume and flow rate. So you can go to the next slide. So on the left shows the calculations of the breathing rate between 5 and 25 breaths per minute. And based on that, the calculations that will come from the breathing rate being set. So the cycle time, the inspiratory time, the tidal volume, in the V dot, which is the flow rate. And then on the right side is the calculation to determine FiO2 rate based on the airflow and oxygen flow, which is set between 0 and 15. And then that way you can calculate what that FiO2 rate would be. These are the user interface for the patient. This is the first patient, but there's a patient for each, there's one for each patient. So this shows the patient name, the ID number, the breathing rate, and the tidal volume, which is set. And the O2 flow rate and the airflow rate will also be set, or which it will be set based on which the calculated volumes are. And then the flow rate diagram, the flow rate waveform chart and tidal volume chart will be the data collected from the patient to make sure the patient is receiving the proper amount of air and that they're having the correct chart that we would want to see for the flow rate and tidal volume.
Taylor, can you go back there? So did I understand correctly that you're inputting the O2 flow rate here with a 5 and the 21.938, and then the calculated below is just an indicator of that calculation, or that's a measured? Which one of those is measured?
The calculated is the measured.
Oh, okay.
So if you go to the next slide, I can explain it.
Okay, sorry.
So this is the code for, so that the coding in the orange is what so like the airflow rate, for the airflow is like going in to calculate all the FiO2 rate. So once that is measured, that is what would be getting reported as calculated. And that's how, so the breathing rate input is why we will figure out what our calculated flow rate will be. Does that make sense?
I think so. You're calculating it from the measured O2.
Yes.
And the airflow rate.
So whatever is inputted for the O2 flow rate and the airflow rate will calculate our FiO2 rate. And then whatever that breathing rate is, we'll calculate our calculated flow rate.
Okay. Right. So at this point, nothing is measured. It's all what we
calculated, but then what is going to be measured will be the waveform charts, which is the flow rate in the blue and the tidal volume in the blue to make
Right.
sure that we're properly collecting the data from the patients.
Yeah. Okay. Cool.
So this is the patient output. The left side with the two charts, there's more charts for each patient, but it's just set so that it'll be easier to fit. But this shows the patient heart rate, which will be collected from the pulse oximeter, and then the blood oxygen level, which will be collected from the pulse oximeter. The the lines on the chart is for an alarm, which is the mask and limit testing on the right, which is an alarm that would be set off if the heart rate gets too high or too low, as well as an alarm for the blood oxygen level getting too low. And this is the diagnostic screen, which shows the pressure for the air manifold and the oxygen manifold, as well as the oxygen level and oxygen tank. One of the masculine testing is shown in the bottom, which is the alarm for the system, which will be collected between a certain set value.
All right, so with the electrical side of things, made a lot of progress for the prototype, and I'll start off with the sensor map, which you've seen before. This just shows where the sensors are, pressure sensors on each manifold, and airflow sensors on the flow going to the patient. Each patient, magnetic sensor to control the blower, and temperature, humidity sensors in the air manifold. Pretty simple, but that was used to make the next slide, which is the flow map. This is the flow of activity for our system. It begins with the patient needing a breath, and that is then we detect a pressure change for the breath. So that's how we know that they want a breath, using a pressure change. And the system then checks the nurse-controlled settings for air requirement and checks the air manifold pressure, as well as also checking the oxygen manifold pressure after opening the air valve for air requirement. Then, as it's also checking the oxygen manifold pressure, it checks the pulse ox, oxygen sensor, data for the requirement for how much oxygen we need. It also checks the oxygen tank to see if we have enough oxygen and pressure. It then opens the oxygen valve for oxygen requirement. Then the system checks for temperature and humidity, and it increases either if it needs it. Then we compare the amount of airflow versus amount of air needed, and then we close off the valves once those are met or exceeded. This may change or grow over time as we learn that more things are needed, but this is definitely the beginning of our flow.
So we're not adding the ability to increase humidity or temperature, right?
The humidifier can do that. Yeah, so we're adding that only because for patient comfortability, because pure air can be from oxygen is really cold. Yeah. Mm-hmm.
Yeah, that's the reason why we got a $150 humidifier instead of a $20 one.
Okay.
Right.
I guess just more responsive.
Yeah.
Mm-hmm.
Next slide. So then we built the timing diagram. So with this, we used a 2-second cycle as an example for just like one breath from beginning to end, what the system's doing. And this is the first rendition of it, so this can change also, and it may change from 2 seconds to 1.8 or more specific, but at this point it's at 2. We begin with the same thing you saw before on the flow map. We just added time to this, and now it's in a chart form. So we're looking to have everything being read from the first 500 milliseconds. If everything is that reactive, it should be. from the sensors we've gotten, it should easily be that reactive. Then opening the valves. I'll get to this in another slide soon, but we did some experimenting on the valves, the solenoid valves, and they're very fast, very fast. It's hard to tell how fast, but they open and close pretty quickly with power.
It's probably more like 50 milliseconds or something.
Yeah, sounded about right. I mean, it was an instant click and instant depressurization, so it was nice. Then yeah, so this may change depending, but this is the timing diagram as we built it. Next slide. This is what we did in person last week. We did some solenoid testing. So the problem that we had, first of all, was that we couldn't find the required amps to operate the solenoids online. The data sheets were kind of rare for some reason. The model number, we couldn't find much on it. So we decided to do a little testing of our own to figure it out, a little bit of engineering. So we created a circuit powering the solenoid, checking the amps drawn in the circuit, just it in itself, and put a meter in series with it, and we found that it uses 0.8 amps. And that's when we found out also that they're very fast. It clicks on and off, and it's very quick. But this was really, really good news for us because 0.8 amps is not much when it comes to both a power supply and also for the power distribution board. It can handle this very well. One line on the power one output on the power distribution board can actually support, what was it? Do next slide. I think I have it on there. Yes, yeah, one does 12 volts to 24 at 10 amps. So we have plenty of room per output. Or sorry, that's the input, sorry. Output is 2.5, excuse me. So yeah, that's still plenty. But this is an updated electrical circuit that shows the updated part is the what's going out from the distribution board and where to and how much is there. Now, each of the sensors won't be 24 volt, I'm pretty sure. So we're gonna, the yellow box to the right shows, says that anything in yellow will use step down circuits to step down the voltages. Those will be buck converters. That'll be in the next update down the road. Buck converters are used to step down voltages safely into a custom voltage of your choice, and I got a lot of practice doing that last semester, so that should be very easy for me to do and to implement in our design. Whether they have buck converters that are purchasable is the question now, or whether I'll have to build them. Either way, it's possible. So I think that's it for me. Next slide.
So this is the pinout diagram for the Arduino. This is an update from the last pinout diagram that we've done. The big thing that we've changed were that we removed the wireless communication and just went instead for a wired communication. The wireless one can be easily added in later if it's needed. But one thing you may notice that some of these sensors are connected to the same pins. That is because we're using the I2C protocol, which allows us to use the same pin because the sensors or anything else that's connected to that pin is operated off an address, and which allows us to directly pull information from that specific sensor or that specific Arduino. One problem we ran into was that the patient side Arduino is a slave to the nurse's station Arduino, which had a problem with our pulse oximeter, which also uses the I2C ports. But you're able to use some of the SPI ports instead of I2C with some minor issues, but that's what we use instead for the pulse oximeter.
Can I ask something? It looks like airflow, oxygen, You know, if you have the same pins listed, I would have thought they'd be different.
Yes, like pins 20 and 21 on the Mega are I2C pins. So the airflow and oxygen sensors, they have an address assigned to them, so that when we read it from our Arduino Mega, we basically said we're reading from this address, and it pulls it from that sensor. Yeah. So like we'll be able to read straight from like patient one's Arduino or straight from like one of the airflow sensors without having to use a different pin. Next slide. All right, this is some of the code that we've came up with. So the left side is the airflow sensor, with the right side being the temperature and humidifier. The right side, the temperature, pressure, and humidifier sensor we've tested, and it works. So this one uses our SPI pins, and the temperature we are putting out is Celsius because most countries are in Celsius, but it's interchangeable. We can easily just put in an extra line to convert it to Fahrenheit. Next slide. And this is a continuation of some of the code. So we have the Mega, and that's supposed to say Nano on the right side, but the Mega is supposed to is the master, while the Nanos are the slaves. So what ends up happening is the Mega is going to say, hey, I need some information from you. And since we're using I2C pins, we can wait for that information to be sent. Versus if we were using any other pins, we would have to do a constant loop, and we wouldn't be able to tell to see if we actually got that information or not. So we constantly say like, hey, I need your information from this address, which we said the address for the first patient is going to be 3, and the second patient is going to be 4, which can be changed as long as both Arduinos know what their address is. And then on the right side, it's just the pulse oximeter code with at the end sending that information that we've collected from the pulse oximeter to the Arduino Mega.
All right, so kind of just looking at what's coming up, some outstanding milestones for the team is just to finish the Arduino code, which as you saw was pretty much almost there, which is really great. We're ahead of schedule for that. And then also the lab view testing, just getting that finalized and ready to go. And then that's next month, the 19th. And then we want to have the ventilator actually assembled and ready to go as well by the 21st of next month, with the first test of the ventilator being the next day. And then we're going to leave a month there for just troubleshooting and getting the ventilator working as needed. And then the plan is by April 21st to have the final test happen and everything be good and ready to go. And then we will complete the project with all the requirements by May 7th, which I think is also the day of the expo as well. Next slide. And then some of the barriers that the team may face. First off, with the budget, as we know, we reduce the number of patients just to better fit the budget and just to kind of get that proof of concept. And then from the electrical side, it's just deciding whether to build custom circuit boards or to buy the needed ones off the shelf, like Billy mentioned earlier. And also just dealing with the power loss with potential long wires as well. And then from the mechanical side, just making sure that everything is fitting together and working together as we intended to do so in the initial design phase. And then with the computer side of things, it's just the distance between the master and the slave Arduino. If it exceeds 1 meter, the data may experience some noise, so we got to find a way to adjust for that. And then also just multiple sensors using the same pin as the slave Arduinos, which I think Noel addressed pretty well. So.
Can I ask you a question? If you did do the wireless, does that solve the 1 meter problem?
Not necessarily. Because since the other sensors are also using I2C, we wouldn't be able to use the wireless communication with those because that would only work with the Arduino. The amount of noise experience from like 1 meter, or like beyond 1 meter, isn't much. It doesn't really get to being a problem until you reach 9 meters, which we are well within the range.
Sure. And you've got opportunities for good cables, maybe that have more grounding insulation and things like that.
Yes.
Yeah. And you've got like the ability to check for the integrity of the data, like you know how much data you're supposed to get back. If you didn't get it, you ask for it again or do something, right?
Yes.
Yeah. I think that's a pretty low risk then. And if you say it's not bad until 9 meters and we're talking 1 meter now, it's good. How long do you expect these cables to be?
Well, since we are having like a minimum of 6 feet, like just between patients, so
2 meters at least.
yeah, 2 meters. The reason why I say like we may experience some noise is we might get it from other devices, not just within the system. So
Okay.
with it being within 1 meter, it's the Arduino experiences a lot less noise and is able to differentiate like this is from like this component. Once you exceed 1 meter, it could be as simple as like someone's phone could easily mess up with some of the communication or a magnet.
Yeah. The decision on the custom board versus buy, has that been made now or we're not sure yet?
The biggest thing was the power distribution board, which we've bought instead of buy. The next one is the buck converters, if we need to buy those or not. But I've never looked into buying buck converters. I don't know if that's even a thing. It might be that I just have to build it, which they're very simple and those are easy to build. We'll see
But
about
you can
that
buy
one.
buck converters.
Can you? Okay, cool.
Yeah.
A question. Would coax cable fix the problem of signal interference?
It wouldn't necessarily fix it, but it can reduce it.
So do you have ways, I don't know, in the lab there with, I mean, we use oscilloscopes, but you can hook up LabVIEW with, you know, analog voltage just to look at what a signal looks like. Do you have access to the hardware that can do that? It'd be like a DAC MX or something like that.
We have some in the, yeah, I think we have some in all labs.
Yeah, I also have my own DAC that we can use to select that.
Oh, nice. Okay. All right.
Okay, so here is just a quick review of the requirements that we had in the performance specifications document. I don't know why that is bi-manifold. It was supposed to say tri-manifold design. It'll be patient-based breathing cycles, so they should be able to somewhat choose what their breathing cycle is going to be, or if not, it'll be based on oxygen level and stuff like that. It's going to keep a mostly constant ventilator pressure around 1.04 atmospheres. All of the air going to and from patients is going to be HEPA filtered just to keep as much contamination out as possible. And then it's going to be a DC powered device. It's going to be 12 to 24 volts, depending on the devices, or rather 5 to 24 volts because of the Arduinos and stuff. And then here we have the performance specs. These are all going to be, or these are all from the performance specifications document as well. So they're just the same performance specs that we had. I did change PS1 up a little bit because we had, I just added budget dependent to the end of it because we were planning on doing 3 patients, but then we found that we might not be able to do it based on budget. But we are going to have to figure that out once we get 2 patients working. And then everything else is pretty much the same as the performance specifications document. Say that again, Roger.
The European standard is closer to 240 volts. And I know that you can buy converters that work equally well with 50 hertz 110 or 50 hertz or 250 volts. Anyway, if you look at the specs, a lot of the world has a different voltage standard than we do.
Yeah, well,
Big 50 hertz versus 60 hertz is any problem. But ideally, when you're picking that DC power source, it should be applicable across the range of AC voltages that are applicable in the world.
gotcha. I didn't actually take a good look at the power supply that Billy was using, but there's a good chance that it has a 110 220 volt switch on it anyway.
I think it does. Pretty sure it does.
So
I could go look at it right quick.
that would solve that problem immediately, I think.
And if not, we can get one. That's just one we were testing stuff with.
Right.
Yep.
So here are the rest of the performance specs. These still just the same. And then we're gonna, next is the budget. So it's really small for you, Roger, but really the main thing here is that currently we're sitting at a total budget usage of $2,079 out of the 3,000. So we're hoping that the remaining 920 will be enough to add in a 3rd patient once we're done testing with 2, but we're going to have to see later on once we get to that point. And now, do we have any questions?
I would like to think that we, have consciously made a few changes to those PSRs or PS1, PS numbers.
Right.
And maybe I can ask, like the director or ISL director, like, it seems to me at this point, like since we've, come into this semester and we've consciously made certain decisions on the performance specs for good reasons. And I wonder if we should make this look, like exactly what we want to do. And anything over that would be, just extra. If we went from 2 to 3, for example. Also on PS3, are we confident that our pressure sensor can measure to that accuracy? And then what does our loop look like to increase the pressure if it's too low or vice versa? It's too high.
First of all, yes,
Uh,
definitely the pressure sensor. We've got it to for that specification specifically.
Okay,
Yeah.
great.
And then for the oxygen loop, pretty much just dependent on the oxygen tank pressure. For the air manifold, that would be probably a mechanical question.
Okay, for the oxygen though, like, so how are you able to adjust that? Is that just a valve, manual valve? Or would that be the airflow?
There's a pressure transducer that'll read the pressure from the oxygen tank, and
Uh-huh.
we're able to change the pressure in the manifold based on how much it needs. We can open and close the valve as needed
Okay.
based on that the readout from the pressure transducer.
So I assume, Billy, that you'll have the outlet pressure, the mechanically determined outlet pressure from the oxygen tank, just a little bit above what you need in the line, and then you flutter that valve to control the pressure. You know how oxygen tanks have two regulators, high pressure and low pressure regulators. I assume that you'll be getting close to the target pressure by a little bit above. Because you don't want to be opening and closing a valve against 15 psi if you need a quarter of a psi. You see what I mean?
Right.
That's the finer point. I'm sorry.
Did you guys understand that? I didn't quite get all that, but
yeah, I didn't quite get that either. Roger, could you repeat what you were saying?
Well, the standard pressure regulator on an oxygen tank allows you to set a pressure. It's not super accurate, but I'm just saying. The regulator itself should be adjusted so that it can be counted on to give a pressure that's just above. If you're going to use the fluttering of the control valve to control the oxygen manifold pressure, you want to have the mechanical regulator set in position so that even if it fails, it won't be overpressure to a dangerous extent. So you got a mechanical backup to prevent overpressurization of the oxygen.
Okay, that makes sense. Okay. I've never worked with oxygen regulators, but I guess that makes sense that they'd be adjustable.
I think that's your only control loop per se, right? You're going to read the pressure and then you're going to manually adjust until you get it to be stabilized or whatever.
Yeah, I was thinking even a little more complicated, like in doing it in code and using whatever pressure we're getting from the tank, but I had forgotten about that it would be adjustable.
Yeah, I mean, it'd be great if if it could be self-regulating.
Yeah.
And that's what the regulator is supposed to do, but it does have to be set. So.
Okay.
Can you go back to the calendar? Yeah. Okay. So are these dates, the 3/19 especially, because that's almost a month away. February is a short month, but still, what needs to be done between now and then? What are we waiting on? What's the long lead item? Does it really take you 4 weeks to finish the code? Because it looks like you've got a lot done, and LabVIEW as well. So is this what the time you think you need, or is this triggered by something else that I'm not aware of?
This is mainly just to give us enough time to make sure that we're getting all of it done and working, and also especially getting it working together, the Arduino code and the LabVIEW stuff,
Okay.
because we have a lot done for both sides, yes, but at this moment, I at least am not confident with putting them together. I don't know how to put them together at all. And so we're gonna have to figure that out, and that's why we're giving ourselves enough time to do that. And we're also going to be working on getting it assembled at the same time, which is
So,
why we have a 2-day lead time for the assembled ventilator.
and that's, I think, another question I'm trying to get, like, is the first two bullets, are they assuming that you're going to actually connect hardware and you're communicating to one another and you're operating valves and things like that, and then assembling the ventilator? So that's just like a benchtop test.
Yeah,
And then assembling the ventilator is actually the tubing and the blowers and pressure,
exactly.
tanks. Okay.
Yeah.
So I think this is good. Then you have everything you need right now for bullet 1 and 2. You don't, right? You don't have all that hardware yet.
We have most of it. I went and picked up a ton of stuff from ISL the other day.
Okay, good.
Yeah.
All right. So then these last 5 POs, or it might have been 6 POs, something like that. Are any of those going to be potential delays, or are they all in stock and all that? Do you know?
I'm pretty sure they're all in stock.
Okay.
Yeah.
Yeah. So yeah, I mean, it looks like a lot to have a month from initial to final, but I can tell you, it'll go fast. And what you said, the expo date was the 7th.
Yeah, I'm pretty sure that's when it is. It's either the 7th or the 8th, but I'm thinking
Yeah.
it's the 7th.
And for some reason, I thought that the some kind of demonstration had to happen before that. Let me see here. I don't know if I can get my calendar up. Let's see. Oh, yeah, the expo's on the 7th. So we should, I'd like to leave time for putting together, some kind of video too. So
Yeah, I think looking at the calendar here, the video is due the week before the expo.
oh, okay. That's what I was looking for. When is all that due? So you're saying basically around the end of April?
Yeah.
Uh-huh.
So,
Yeah, that's probably doable. Well, certainly, you guys have made great progress. First of all, I'm really pleased. I feel like, you got things ordered, you got code, really working, LabVIEW's working. And you know where you're going with all the inputs and outputs and what's being calculated and things, and the calculations look good. How do you feel?
Confident that we can get this done.
Okay, good. Like you can actually kind of see the through line there.
Yeah.
Okay, good. That's how you should feel. Yeah, I feel pretty good about it, I think. I just want to make sure we leave enough time for debugging and testing. And at least I think what you're not showing on here is that before bullet 1, you're actually doing a fair amount of test and debug and integration between Arduino and LabVIEW before the 19th. Like that's happening in this week, next week, right?
Yes.
Yeah. Okay, good. I'm glad to hear that. Okay. Because yeah, I certainly don't want to see us bringing, those two together on the 19th and assembling and expecting it all to work.
Yeah, that should be starting up this week. And then those are just kind of, I guess, hard dates that it's got to be done by. So
Yeah, I understand. And those are basically like release dates, if we would call them in industry. We would say they're, we've already had beta testing and rounds of, updates, and now this is really release dates. Yeah. Is there anything that can be done to assemble the ventilator mechanics before the 3rd week of March?
yeah, I'm planning on maybe me and Taylor next week getting together and starting to put together what we can. So
Okay. That'd be good, I think, just because if there is something that you didn't realize you needed, you could, you still have time to order and get. And you got the budget left to do it, which I think is great. I mean, I think you're setting yourself up for success because you've got, time if you have to change something, to get new parts in, and you got budget to do it. And yeah, I mean, I think just keep up the pace. I mean, I don't know if you feel like you can hold this. Do you feel like the pace you're at is maintainable, or do you feel like, no, I got to stop today and get back to my other classes?
I'm kind of in the middle.
Okay.
Today I have something due. Tomorrow I have something due. Friday I have something due.
Mm-hmm.
So I can work on it in between.
Yep.
But it's not, I can't just drop everything and work on just this.
Mm-hmm. Mm-hmm. Okay. And who's kind of taking responsibility for some kind of test plan? We ordered the balloons, right?
Yes, we got elastomeric.
Yeah.
Yeah.
Yeah, we did.
But I can take control of testing if that's needed.
Okay. Yeah, just would be kind of nice to know, like when you present, the final report in the expo, like how did you prove that it worked? How many, breathing cycles does it take to show, that the pressure stabilization is there, the temperature, humidity, that you can change the dials and that they respond quickly enough or whatever. I don't know. I'm just throwing things out. I'm not suggesting anything necessarily. I'm just thinking we need to kind of have something that says, okay, we passed this, we made it. And I think those can be part of, they should be part of the expo story that you tell in the video and so forth. Yep. What about portability? Like, is there anything we're doing to, I don't know, kind of figure out how it could be a packaged device? It's probably low on my totem pole just because I want to make sure it works well, but will it fit in a breakdown into a 3 by 3 foot pallet crate? And how much would that weigh? I don't know. Might be something to think about.
Yeah, we can definitely figure that out. That I would say that's also pretty low on our end as well.
Mm-hmm. Okay.
At least the box with the Arduino Mega is going to be relatively small.
Hmm.
The Mega is like that big, so
Yeah. Yeah, so we're putting them in a metal enclosure, is that right?
I believe that was the plan.
Mm-hmm. Okay, it's been ordered.
Um, that hasn't been ordered, but I think that one we were planning on going through uh, the manufacturing lab here. But I haven't gotten anything from Jacob or Taylor about that yet.
Yeah, we can look into that this week and get that all figured out soon.
Yeah. I mean, for right now, all your testing it's just splayed out all over the table, right?
Yeah.
Which is fine. Which is fine. But
Yeah,
at some
we're
point,
we're literally planning on just benchtop testing probably until the very end.
yeah. Well, yeah, no, I would try to, I mean, we got to have it packaged up, right? It can't just be splayed out all over the table in the end. So
Right.
let's plan on getting a box in, getting it, because it's gonna need cutouts and, you know, it needs a design. I mean, even if it's only USB ports or whatever, or cutout for a cable. But we need to make this look nice, and we really should have those drawings done. You know, we're buying this box off the shelf, and we have to cut out, you know, this on these sides, and then get that done. I hope it's not. I don't think it's that critical, but I mean, there's some projects where you're gonna have to have, you know, this cutout for a DB9, and this cutout for a USB, and this cutout for a coax, and you know, or you know, network connection or something.
Mhm.
And a switch for the box and things like that. I don't know if we need all that, but you know, is there anything like on the Arduino boards that you might have to get to? Like if it's in the box and you need to hit the reset button, you know, can you get to it? Or does it have to be mounted so that the reset button is accessible from the outside? Or you know,
It's a board mounted reset button,
okay.
and reset buttons are like cents. So they're super cheap. So
Yeah.
I probably won't even submit a purchase order for one. I'll just buy one.
Well,
Um,
so how do you
I-
get it from the box reset
we
button?
can
Can you wire that?
we can just wire it in. We can solder wires onto the board
Okay.
and jump them to the actual reset pin, or we can actually stick it in on the pins that are on the board.
Yeah, I mean, ideally, you know, it'd be nice if you could just put standoffs on the box and then let the reset button just be accessible through a hole in.
Yeah, but the problem is the reset button is like right in the middle of the board,
Oh,
and
okay.
it's also super small.
Okay.
So
Right.
it's kind of non-ergonomic to get to it. You'd have
Yeah.
to you'd have to like mount the board up against the thing, but then that would also block the pins that you need to stick
Uh-huh.
wires in. So
Yeah. I mean,
kind of counterintuitive.
it's common for us to build little, you know, plastic injection molded, you know, pipes, so to speak, that go, you know, from the middle of the board like that, where it needs to push down, you know, all the way up to the top of the box, and it just sits proud up there, so that, you know, when you want to reset it, it can do that.
I didn't
But
even think about that. That would be a good idea, actually.
well, it's probably not worth the design effort at this point. If you can do the same with an electrical button, I mean, a mechanical, you know, if you can do the same with wires. But
Right.
I'm just saying, like, if you were designing for, you know, manufacturing, you'd probably do that, because nobody wants to solder wires in manufacturing. It just costs too much time and money. So,
Right.
yeah. Wow. Okay. Well, very good. You have any questions for me or Roger?
I don't think so. Michelle, would you like to do a mentor meeting on Friday?
Sure. And I'm sorry if I missed one last Friday. For some reason, I thought we were not doing anything until this
Yeah,
Monday.
I think it was just miscommunication.
Okay.
I assumed that we were gonna do it even with our presentation today,
I see.
but yeah.
Yeah, I'm sorry. I was skiing. I wasn't
That's
even
worth.
checking emails, so my bad there. I just
That's
thought I
worth
was,
it.
Yeah,
yeah, I thought I
definitely
was
worth
there
it.
till Monday. So anyway, well, it sounds like you did your own, figuring it out. So this looks
Yeah.
great, and I think y'all did real well. So
Cool. All right, well, I am going to pause the recording now, or stop the recording now. And